Bismillahirrahmanirrahim. In this, you can see clearly this one is core, iron, iron ferrite core, right? Core. And this one is coil. So see, you are going to wound the core. You start from top to bottom. This is the winding, right? See, it seems exactly like coils, right? Or another way, you can. It was from top to bottom. You can wound this core from bottom to top. See, bottom. In this case, you are wound your coil from bottom to top, right? So the current may flow. The current flow in the coil may be top to bottom and from bottom to top, right? In both the case, the magnetic flux lines, the magnetic flux direction changed. If the current flow from top to bottom, the magnetic flux are upward, the magnetic flux are upward, and if current flow from bottom to top, the magnetic flux is downward. Or remember like this: if current go downwards, flux go upward. If current go downward, flux go upward. If current go upward, flux go downward. Right? The car go forward, the smoke of the car go backward. Remember like this. Consider the example of a transformer. In transformer, we have two sides: primary side and we have a secondary side. Voltage supply is given to primary side. Let's suppose supply is given to primary side with the polarities plus minus of V1, and the current will flow in the secondary primary side, that is I1, due to supply voltage V1, and the flux is set up in the primary, that is phi 11, self, because it's influence only is itself, right? So phi 11. Similarly, current will flow if you connect the load on the secondary. Connect the load on the secondary. There is voltage induced in secondary coil, and that is current flow in the secondary winding I2. And now here we going to understand the dot convention, right? So I will put my dot here, right, and I will put my dot at here. See, in both the in both the windings, that is primary winding and secondary winding, both the currents are entering into the dotted terminal of their windings. See, primary coil and secondary coil means coil is wound from top to bottom, and current flow in both the circuits is in dotted terminal. So if a current enters the dotted terminal of one coil, the reference polarity of the mutual voltage is second coil is positive at the dotted terminal of the second coil, right? So in this configuration, the mutual inductance in the secondary coil is positive because the configuration being same, that is both the currents are entering into their dotted terminals. So this one is phi 21, right? Phi 21, and this one is phi 12, right? Because we have phi 21 mutual of that is linkage of coil primary coil on 2, linkage of secondary coil and coil 1, right? Mutual inductance. So there are four fluxes, right? That is flux due to coil 1 and it links to coil 1, flux in coil 2 phi 22, and it links with the secondary coil, that is it links itself. Now the mutual fluxes, that is the flux generate from primary links to secondary, the flux generate from secondary links to primary. Phi 21 mutual of secondary coil on 1, mutual on of primary to coil 2, right? So I hope you understand. So we simplify this like we can draw a simplified circuit, that is coil 1, coil 2, coil 2. We put our dot at top, that is top terminal. This one is mutual inductance, right? This one is current in one coil, that is voltage induced in second coil, that is change of current in primary coil, that is change of current in coil 1 induce a voltage, that is mutual voltage, right, in secondary coil, and it's sensed positive. Why? Because see the configuration, the dots are placed at the top of both the coils, right? So mutual being positive. Second case, in second case what I did, yes, you can guess what I did. Yes, I alter the dot. In first case, the dot was placed at top, but now in second case, the dot is placed at bottom. So the mutual inductance so the mutual induced voltage in secondary coil is nothing V2 times minus di1 over dt. Why this minus? Well, minus because the configuration changes. See, the coil construction changes. This coil is wound from top to bottom. It's wound from top to bottom. This one is from bottom to top. So the configuration changes. Means current also changes. So the mutual inductance, the negative sign appears negative in the mutual, right? Now consider the we in both the cases we consider primary current. Now consider secondary current. I2, and this one is dot, and this one is dot, and this one is mutual, this one is mutual. So this time current enters like this. See, what is the voltage induced on primary? Can you guess what is the voltage induced on primary? It's positive or negative? Yes, negative. Why? See, the configuration changes. So it is nothing but minus M due to change in current coil 2. Mutual inductance in induced voltage on primary side due to change in current in secondary coil. It is minus because the dot convention is changed. That is, one coil is wound from top to bottom, other coil is wound from bottom to top. So the induced voltage becomes negative. Same case. Now the last case. Last case. The last case, you see, I have changed the dotted. The see, it's like first case, but in this case, the last case, the dot is put on the bottom of the coil, right? So the induced voltage on primary side is positive or negative? Yes, is positive. Why? Due to change in current coil 2. Induced voltage due to change in current in coil 2 to primary side, that is V1 side. It is being positive. Reason? The dotted, the configuration being same. Remember, when the configuration same, then the mutual appears positive. When configuration opposite, then mutual appears is negative, right? In these cases. In this case, the configuration being same. How same? Because dot, both the coils are having their dots on their bottoms. So the mutual being positive, right? Now, if we consider the series connection, what is series connection, student? Remember, series connection is that when two elements are connected, for example, this marker, and this, for example, this marker and this uh, b- um, duster, right? If two elements are connected to end at one end, and there is no third element is connected over there, this is series connection, right? Two elements are connected at one point, form a node, and no third element is connected over there. This is the definition of series. And what is parallel? When two elements are connected end to end. When two elements are connected end to end, this one is parallel. This one is series. See, this one is series, and this one is parallel. So, in series, when two coils are connected such that one coil and the second coil, see, they are connected, both the ends of the coils, both the ends of the coil are joined together, and there is no third element connected over there. This is being series connection. And I put the dot like this. The dot I put like this. The current flow in this, right? And the current flow is like this, and the mutual between these two is like this, right? So this one is L1 coil 1, this one is L2 coil 2. So the current flow in both the coils entering into the dotted terminal, entering into the dotted terminal. So what is the mutual? Mutual becomes positive because configuration is same. So what is L? That is total L, that is L1 self inductance plus of L2 self inductance of coil 2 plus 2 times mutual. The mutual of this coil on this and the mutual of this coil on this, and mutual is same and positive, so plus 2 times M. This is series adding convention, right? This is series adding convention. And what is series opposing connection? For example, in this configuration, if I remove the dot from this place and I put the dot at this place, see, before the dot was placed at the starting of the coil, now the dot is moved to end of the coil. So if the coils are, if the dot convention is like this and they are in series connection, the what is your L? L is what? L1, obviously self, their self inductance minus 2 times M. Why minus? Because mutual of this coil on this coil is negative, mutual of this coil on this coil is negative. Why? See, the current entering into the dotted terminal of this coil, while the current entering in the undotted terminal of this coil. See, undotted terminal. So the configuration is changed. So the mutual becomes negative. That's why minus 2 times M. Mutual becomes negative. I hope you understand. Now consider a practical circuit. For example, a circuit while having a supply in the circuit, that is supply, AC supply V1, right? And a resistance is connected, resistance, and a coil is connected, coil, and it forms a closed loop. What is mesh? Mesh or closed loop, right? Same. So this one resistance R1, this one is supply voltage, that is V1, and this one is inductance, that is L1. I put the dot over here, and secondary coil, secondary coil. The resistance, actually this resistance is the internal resistance of the coil actually. So it was hidden before, now it shows to you. This one is the resistance of the secondary coil R2, inductance of the secondary coil L2, and it is connected with a supply, that is plus minus V2, and it forms a closed path. We have two mesh circuits, that is this coil is fed from supply 1, that is V1. This coil is fed from supply 2, that is V2. And we know that current flow from positive terminal to negative terminal, because positive terminal has higher potential, negative terminal has lower potential. So current flow from positive terminal of the supply to the negative terminal. So in this circuit, the current flow like this, the loop, it forms a loop, and current flow like, and this current is nothing but I1, because it flows in circuit 1, loop 1, mesh 1, right? This one being the mutual on these two, M, right? This one is M. And in this circuit, the current will flow again from positive to negative, the current flow I2, right? and I placed my dot at here, right? Now we have to write the KVL equation for these two meshes. We have to write mesh 1 and mesh 2 KVL equation. What is KVL? Voltage rise is equals to voltage drop, right? So write the KVL equation for mesh 1. For mesh 1, KVL Kirchhoff voltage law equation. Mesh 1, the equation becomes what the equation V1 equals, right? Voltage rise equal to voltage drops. So V1 equals to I1 times R1 plus L1 times di1 over dt, right? Plus M mutual due to secondary current on primary, and this one for loop 1. Okay, this one was mesh equation for loop 1. What is the mesh equation for loop 2? Loop 2, yes, what is the mesh equation for loop 2? V2 is equals to, in loop 2 we have current I2, R2 times R2 plus L2 times di2 over dt plus M di1 over dt. Remember, when you write the mutual term, see, this one is V1, the mutual is due to coil 2, and this one is V2, the mutual is due to coil 1. So remember this. So this is the time domain analysis of a circuit containing coupled coils, right? Time domain analysis. We can do frequency domain analysis as well. Why it is mutual is positive? Why mutual is positive? Yes. See, in loop 1 the current enters, current direction, the current enters into the dotted terminal of coil 1, right? While in mesh 2 the current enters in the dotted terminal. That's why mutual appears in both the equation being positive, because entering of the current is in dotted terminal in both the loops. Note this. The frequency domain analysis of closed circuit containing coupled circuits is like, again, you will draw the circuit, that is supply, that is V, and this one is impedance. Impedance is a combination of resistance and reactance. So we termed this term as impedance. This one is coil, and this one is j omega L1. We place our dot like this. Now secondary coil. Secondary coil. We place the dot like this, j omega L2, and we put our impedance, that is Z2. This one is Z2, means supply is given to primary side and current will flow due to load in the secondary side. So dot is placed like this, so mutual of these two, mutual of these two, right? So again write the KVL equation. You will get V1, this one is V1, V1 is equals to, in KVL the simplest form is to you add up all these resistance and reactances, and you minus the other, right? In loop equation what we write, we consider, if we consider loop 1 current is greater than loop 2, so the loop 2 appears negative in the equation, right? And when we write loop 2 equation, loop 1 current appears negative, and vice versa, right? So V1 is equals to, just sum up, plus R1 j omega L1, this is frequency domain, right? And it's times I1 plus j omega M I2. Why I2? Because this one is V1. This one is mutual term, and we are writing equation of loop 1. So loop 1 we have a current. See, we have a current like this. In loop 2 we have a current like this. So mutual becomes positive. Mutual becomes positive, right? because both the currents are entering into the dotted terminal. Similarly, V2 is equals to J omega M times I1, because V2, this one is I1, mutual due to current 1, right, on coil 2, and so on, plus R2 plus J omega L2 times I2, because it was loop 2 current, so all the impedance and resistance are right with the equation with loop 2 current. This one was loop 1. So this is being the frequency frequency domain analysis, right? Now if we as a second example, consider the circuit in figure. If we consider sorry students, these equations are for the circuit which was drawn before, right, in the before, and before this the configuration was same, that's why mutual in both the cases being same before I draw the circuit, right, not for this. For this the mutual, I will write the mutual, right. This is the frequency domain representation of the circuit drawn before. Now for this circuit, the what is the equation, that is V equals, right, this one was before, not for this. For this circuit the equation becomes V is equals to Z1 plus J omega L1 times I1, right. Z1, this one impedance, this thing, right. And remember also, frequency domain representation we use capital letters, time domain representation we use small letters. So now I'm writing the mutual term. So mutual term is positive or negative? Yes, students, it is negative. Why? See, the current entering in the dotted terminal of this coil, while the current entering into the undotted terminal of this coil. So mutual appears negative. That is minus of J omega M I2. This one is V1. See, this one is V1 and mutual due to I2, and this is minus sign, right? And what is the mutual on the sorry, KVL equation for loop 2? This one is loop 2. So in loop 2 there is no voltage source, so the left hand side becomes 0 and the right hand side becomes J omega M times I1 plus, because in secondary side we have a impedance that is ZL or Z2 for example, and we have a self inductance that is J omega times L2 and multiply by I2. This is loop 2 equation. And this mutual is positive or negative? This mutual is negative. Why? See, in this circuit the current flows in the undotted terminal, right, and this current flows in the dotted terminal. Configuration is changed, so mutual appears negative. Mutual appears negative. See the configuration of the current. The current flows in the undotted terminal of this coil, while the current flows in the dotted terminal of this coil. So mutual in this case is negative. See, mutuals are negative. So these two equations are for this circuit. I hope you understand. Let's do an example. Let's do an example, and we have a values. That is this one is supply, and this one is 12 0 degree volts, right? And here is capacitance of minus J4 ohms, minus J4 ohms, right? And we have inductor connected in series, and we put our dot here. This is J5 ohms, right? And current in this loop is like I1. And this circuit, and the secondary circuit, is connected with the load of inductance and resistance. The resistance of the value of 12 ohms and the inductance of the value of J times 6 ohms. And we put our dot here, and current flow in the secondary coil is like this. See, both the current directions are same and dots are placed, right? So calculate the phasor currents I1 and I2. You have to calculate the phasor current, that is I1 and I2. Okay, mutual is also given to us. In this circuit, the mutual is given to us, that is J3 ohms. So for for loop 1 KVL, for loop 1, what is the KVL equation? For loop 1, the KVL equation becomes, for example, this one is minus 12. Okay, voltage rise is equal to voltage drop. You put your source at this side, right? Voltage rise is equals to voltage drops. So by putting the source value at one side, 12 equals, what is this? This is minus J4 plus J5 times I1. And now we have to write the mutual term. For mutual term, mutual is given to us, that is J3 ohms. What is the mutual term? Positive or negative? See, this current and this current, the current flows in the dotted terminal in this loop. See, the current flows in the dotted terminal of coil, and for this, the current flows in the undotted, the entrance of current. See the direction of the current, the entrance of the current in undotted terminal. So the configuration reverses, configuration reverse. So mutual becomes negative, right? So mutual term become negative, that is minus times J3 I2. See, this one is V1, so the mutual becomes I2. So just rearrange, you will get Ji1 minus J times 3 I2 is equals to 12. Equation 1. Now come towards equation 2, loop 2, right? KVL equation for loop 2. What is the KVL equation for loop 2? See, 12 plus J6 times, because loop 2, so current I2, right? So this is self term. What is mutual term? What is mutual term? It is again minus 3 times J, but now I1, because loop 2. Mutual due to, in this coil, mutual due to current, change in current in this coil, right? So mutual appears I1, right? Vice versa, means in loop 1 there was I2, in loop 2 the mutual is I1. Why minus? Because the current enters in undotted terminal. See the entrance of the current. In this loop, the current enters into the undotted terminal of 6J ohms Henry, while the current entering into the dotted terminal of J5 ohms. So mutual becomes negative, minus J3. So just rearrange the equation. Means you have two equations. This one is equation 2. So you will get the phasor current, that is I1. I1 equals so you just put the values. You just put the you just need to substitute the values. J2 plus 4 minus J3 I2 equals 4 minus J I2 equals 12, right? You substitute in terms of I2. So I2, that is secondary current, is nothing but 12 over 4 minus J equals, if you convert into rectangular to polar form, you will get I2, that is 2.91 angle 14.04 degrees. The unit become ampere, and you just put the value of I2 in equation 1, you will get the current I1. So I1 becomes, you solve 2 minus J4 I2 equals 4.472 angle minus 63.43 degree times 2.91 14.04 degree. So finally you get your current I1, that is 13.01 angle minus 49.39 degree, and the unit becomes ampere. So that's we calculate our currents, right? Our phasor currents. I hope you understand this problem. Thank you.